So good morning, everyone, and welcome to today's lecture. This is lecture number 3, and we are dealing with radioactivity. In the previous class, we had seen how you can find out the Q values of different reactions and how you can find out the different types of decay. We had seen alpha decay, beta decay, and gamma decay. In alpha decay, helium nucleus is given out. In beta decay, there are two types of beta decay: beta minus, where an electron is released, and beta plus, which is very rare. Gamma decay, it only happens after a alpha or a beta decay. After an alpha or a beta decay, the nucleus which is produced may be in a higher excited state. It will come down to its ground state. It will emit some radiation, photons. Those are gamma rays. Now, in today's class, we will go and see the last part of this, which is known as radioactive decay. Now, we will see when a radioactive or a unstable nucleus decays. We have seen that it will decay spontaneously. Now we will see the rate at which it decays, what is the number of particles and how much does they decay. The first thing here we must understand is the law of radioactive decay. Now, what are these laws of radioactive decay? You might be aware of this law of radioactive decay. The first law, or the first thing that you can see here, what happened? The first thing that we can see here is, we have already discussed this radioactive decay or this radioactivity is a spontaneous process. This radioactive decay is a spontaneous process. It just happens. An unstable nucleus will convert itself into stable nucleus by the emission of alpha, beta, and gamma rays. It is not influenced by external condition that external pressure is put, then only it will happen, or if the temperature reaches this amount, then it will happen. No, it is not influenced by this. At any temperature, at any pressure, in presence or absence of magnetic field, radioactive decay just depends on the stability of the nucleus. It's a nuclear process. I must tell you that it's a nuclear process. Now, the second law of radioactive decay was given by Rutherford and Soddy. This is known as Rutherford and Soddy's law. Rutherford and Soddy's law of radioactive decay. And in short, I mean, not in short, even if in explanation, we will explain it like this: the rate of disintegration, Rutherford and Soddy law. The rate of disintegration, the rate at which the nucleus disintegrates, is directly proportional to the number of radioactive atom present at that time. That is, the rate of decay is directly proportional to the number of nuclei. So basically, if I call the rate of decay as R is directly proportional to the number of nuclei that are present. Now this R, rate of decay, is sometimes also known as activity of the sample. So I may write it as A also. Or this R will be the rate at which the sample is decaying. So I can also write it as dN by dt. dN by dt. So this law simply says that dN by dt will be directly proportional to n. dN by dt, the rate at which the nucleus decays is directly proportional to the number of nucleus present at any given time. I hope you understand what I am saying. Now, if I remove this proportionality sign, I will have this revolutionary equation dN by dt, which can also be called as the rate, which can also be called as the activity A. We will see that in definition will be equal to minus lambda n, where lambda, my dear friends, would be a constant, where lambda is a constant and it is known as the decay constant. Lambda is a constant. Lambda is a constant, and this constant is known as the decay constant. Lambda is a constant and it is known as the decay constant. I hope up till here everything is clear. I'll give you 2 minutes to note this down. The law of radioactive decay given by Rutherford and Soddy simply tells us that any point in time, the rate of decay is directly proportional to the number of radioactive nucleus present at that given time. dN by dt, which is also known as the rate, sometimes we also call it activity, is minus lambda n. I'll give you a minute to note this down. Now, this decay constant lambda is different for different radioactive substance. It does not depend on the amount of substance and time. So, it's the constant for a given substance. It does not depend on how much substance is remaining or how much time has elapsed. It only depends on the radioactive substance that is present. Another important factor, the unit of lambda is 1 by second, same as frequency, 1 by t. If lambda 1 is greater than lambda 2, then the first substance is more radioactive or less stable than the other one. It is very simple to understand. I hope all the points are getting clear. Now, let us take the example and what is the type of question that you are going to get. You will have one radioactive substance A and it will get converted into another substance which may be radioactive. If B is also radioactive, it will again get converted into another substance. We call it successive disintegration. We will see that. Anyways, let us take the example of a radioactive nuclei A getting converted into another stable nuclei B. The rate, the decay constant, the constant for this reaction is lambda. So you can see here at time t is equal to 0, the number of nucleus of A is n naught. We call it n naught at time t is equal to 0. 0 means naught. And the number of nucleus of B is 0. At any given time t, the number of nucleus of A is n and the number of nucleus of B which is formed is n dash. I hope you understand this. N naught is the initial number and n is the number at time t. The rate of decay of A, the rate of decay of A, dN by dt can be written as minus lambda n. Now you can easily integrate this equation, which I am not getting into this. You can easily integrate this equation and you will end up with this result. The number of nucleus of A remaining after a time t will be given by n is equal to n naught e to the power minus lambda t. I hope all of you understand this. You can just raise your thumb in the chat so that I can see it. The number of nucleus or nuclei of A remaining after time t will be given by n naught e to the power minus lambda t. Do we all understand this? Do we all understand this? Do we all understand this? Are we there in the class? Okay. Now the same equation, we have written it in terms of number of nuclei. We can also write it in terms of mass. M is equal to m naught e to the power minus lambda t, where m is the original mass, m is the mass of the nucleus, mass of the substance remaining after time t, and m naught is the original mass of the nucleus. Original mass of, not the nucleus, original mass of the substance. Now, if we talk in terms of what is the number of nuclei of B which is formed, number of nuclei of B will be given by n naught minus n. That will be the number of, this number of nuclei decayed will be same as the number of nuclei of B formed. I hope you understand this. Yes or no? So the number of nuclei of B which is formed will be given by this revolutionary equation. N dash is equal to n naught into 1 minus e to the power minus lambda t. N dash, number of nucleus or nuclei of B which is formed, will be n naught into 1 minus e to the power minus lambda t. As soon as you see this equation must remind you of some other equation which you have done already. Do we remember that equation? I'll give you 2 minutes to note this down. Well, then these are the graphs that you can draw. The first graph is between n and t, the number of nuclei of A remaining as a function of time. The second graph is between the graph of n dash and t. N dash is the number of nuclei of A which has disintegrated, or in other words, the number of nuclei of B which has been formed. The third graph has both of these graphs drawn together on one x and y axis, and you see some important terms here, TH, TA, and we will understand these terms TH and TA when time comes. I will tell you. I'll just now after this. Now remember the various ways in which you write the equation. The first way you write the equation is dn by dt is equal to minus lambda n. This is also known as the rate of reaction, or as you will see, it is also known as the activity of the sample. Activity of the sample. Activity of the sample. The second way in which you can write the same equation is log of, look at it very carefully, log of n by n naught is equal to minus lambda t. This is the next way in which you can write the same equation. I hope you understand this. N is equal to n naught into e to the power minus lambda t. This is the third way in which you can write the same equation. Now, many a time you might be asked to find out the time. Time can be written as 1 by lambda ln of n naught by n. I've reversed this to get the negative sign out. It is in terms of ln, so you can write it as 2.303 by lambda log to the base of 10 and naught by n. I'll give you 2 minutes to note this down. I hope all of these terms are pretty simple and pretty straightforward. I'll give you 2 minutes to note it down. The next heading, or the next thing that we are going to understand is half-life, T-half. Sometimes in some places you may also see it as TH or T small h. This was a very popular video game, computer game. At some point in time, I played it a lot, but that has got nothing to do with a computer game. The computer game was something different. Half-life. What do you mean by half-life? And the meaning of this half-life is hidden in the heading itself. What would be half-life? What would be half-life? What would I call the half-life of a radioactive nuclei? So, half-life of a radioactive nuclei would simply mean the time interval in which the mass or the number of the atom or the nucleus, it reduces to 1/2 of the original mass or the original number. So if at any time the number of nucleus n becomes n naught by 2, then time is known as t half. Then time is known as t half. I hope you understand what I am saying here. So now if you put this n is equal to n naught by 2 in the original equation that we have seen, n is equal to n naught e to the power minus lambda t. Instead of t, it will become t half, and from there you will get the value of t half, and the value of t half is sorry, can be written like this. This is nothing but natural log of 2 by lambda. You can also remember it as sorry, 0.7 divided by lambda, t half, the time in which the number of nucleus becomes half. I'll give you a minute to note this down. You can also draw this graph together with this. This graph shows you the value of n in terms of t time. And as you can see, if I take the half-life as capital T, if I take the half-life as capital T, after one half-life or 1 times T, the number of nuclei that will be remaining will be equal to n naught by 2. After time 2 times of half-life, 2 half-lives have gone, the number of nuclei will become n naught by 4. After 3 half-lives have gone, the number of nuclei that will remain will become n naught by 8. That means after every half-life, the number of nuclei becomes half of the value. So I can write it like this. I can write it like this in terms of this equation. If n is the original number of nuclei, if n naught is the original number of nuclei after first half-life, the number of nuclei that would be left would be n naught by 2. After the second half-life, the number of nuclei that would remain would be half squared. After the third half-life, the number of nuclei that would remain would be half raised to the power 3. So the number of nuclei remaining after n half-life, the number of nuclei remaining after n half-life will be equal to n naught into 1 by 2 raised to the power small n. Remember, this small n will be equal to time divided by t half. This small n is the number of half-lives. Do we understand this? Can I have raised hand that we understand this? Number of nuclei remaining after n half-lives would be n naught into 1 by 2 raised to the power of n. I'll give you 2 minutes to note this down. So coming back to the same fact, and this is the table that I have drawn. After n half-lives, the number of undecayed, those who have not decayed, will be given by this revolutionary formula. This is a very important formula that is going to help you in a lot of questions. Or you can write this same formula in terms of t divided by t half. Remember, this n may be a fraction also. It may not be an integer, it may be a fraction also. Then also this formula holds. Now this is a table that I have drawn. At time t is equal to 0, it is n naught. After 1 half, it is n naught by 2 and so on. This is known as probability of survival, remaining fraction, n by n naught, and the fraction of atoms decayed is known as the probability of decay. So you just divide n by n naught, you will have the probability of survival. You will divide n naught minus n by n, which is the number of half-lives, n by n naught, and you will get the probability of decay. Nowadays, these things are not asked, but this is just for your information. If you want, you can note them down fast. Then let us move on and solve this simple question. These are the type of question that are going to come in your exam. A radioactive sample has 6 into 10 raised to the power 18 active nuclei at a certain instant. How many of these nuclei will be in the same active state after 2 half-lives? So how are we supposed to solve this? It is given that initially there are 6 into 10 raised to the power 18 active nuclei. So that becomes your value of N naught. It has been asked what is the number of active nuclei after 2 half-lives. The formula that you have to use is N is equal to N naught divided by 2 raised to the power of N, where N is the number of half-lives. So the number of active nucleus will be 6 into 10 raised to the power 18 divided by 2. The number of half-lives is 2. So the answer is 1.5 into 10 raised to the power 18 will be the number of active nuclei after 2 half-lives. I'll give you a minute to note this down. Once you are done, please let me know. Let's move ahead and solve this question. Again, it's a straightforward question. The number of U-238 atoms in an ancient rock equals the number of lead 506. The half-life of decay of U-238 is 4.5 into 10 raised to the power 9 years. Estimate the age of the rock, assuming that all the lead 206 atoms are formed from the decay of uranium U-238. I'll give you 2 minutes to solve this. So what is given in this question? The number of U-238 is same as the number of lead Pb206, and we have to assume that all Pb206, because Pb206 does not occur freely in nature, all Pb206 have come from uranium U-238. That means initially you had only U-238 and lead Pb206 was 0. This uranium U-238 has converted into lead 206 and all of lead has come from uranium. Now both the numbers are equal. That means whatever number of lead has come, it has come from uranium. So initially the number of uranium nucleus must be 2 times of what the value is. That means half of the uranium U-238, half of it gets converted into lead. Half of uranium U-238 has converted. How much time will it take for uranium U-238 sample to convert half of the nucleus into lead? It is equal to its half-life, and therefore the age will be equal to the age of the sample will be equal to the half-life, and therefore the answer is 4.5 into 10 raised to the power 9 years. 4.5 into 10 raised to the power 9 years before it only had uranium U-238. 4.5 into 10 raised to the power 9 years after today, it has half uranium and half lead, because half of uranium has converted into lead. This is the answer that I was looking for. I'll give you a minute to note it down. I hope you have understood this concept The concept is pretty simple and pretty straightforward. That takes us to the next heading, and the next heading is known as average life. Average life. Sometimes it is written as TAVG, or I may write it as T in a dabba. Remember that dabba? The dabba is the average. What is T average? Now you can define it in different ways. The first way you can define it is the time for which a radioactive material remains active is known as its mean or average life. This is one way of defining it. This is way number one of defining it, but this is not the only way of defining it. It may be defined as the sum of lives of all the atoms divided by the number of atoms. So I can also write T half, or sometimes it is also written as tau, T half or tau as sum of life of all atoms, sum of life of all atoms divided by the number of atoms. Now, if I do this, sum of lives of all nucleus and divided by the number of nucleus, I will get an equation which looks like this. And the value of this T average will come, don't look at the integral, the value of this T average will come simply equal to 1 by lambda, my dear friends. 1 by lambda, 1 by lambda, 1 by lambda, 1 by lambda, 1 by lambda. So this is the second way of understanding this. Now the third way of understanding it is in the form of the graph. If I draw this graph, a graph between ln of a graph between ln of n versus n naught n time t. The slope of this graph, you must remember that I had written ln n by n naught as minus lambda t. So basically, the magnitude of the slope of this graph ln n versus n naught and t, the slope will be equal to minus 1 by lambda. If I find the slope will be equal to minus lambda. If I take the magnitude and I inverse it, that will be equal to the average life. Do we understand this? Since there is no space left, I'll give you 2 minutes to note this down. Well then, we can look at the next one. From n is equal to n naught e to the power minus lambda t. If I put time as 1 by lambda, which is nothing but equal to tau or t half t average, we will get that the value of n will come as 0.37 and naught. This number 0.37 and naught should remind you of something that we have already done. I just don't want to get into that. 37% of the nucleus, when it remains active or undecayed, or it becomes 1 by E times 1 by E is 0.37, then we call that time as average life. Or it is the time in which the number of decayed atoms and not minus n, my dear friends, and not minus n, my dear friends, and not minus n, my dear friends. This n naught minus n becomes 63% of the number of decayed, or the number of the next nucleus which is formed is 63% of the original number. That time is known as the average time, average life. You can also draw t half is 0.69 by lambda, but 1 by lambda is tau. So you can now write t, you can write tau in terms of t half in terms of average life, or t average in terms of half-life, t average, or tau. This is what I remember is 1.44 times t half. So 1.44 times t half is your tau, or it is point, or t half divided by 0.693, different variation iteration of the same formula. That takes us to the next heading, activity of a sample or decay rate. You can call it as minus dn by dt, you can call it as r, you can call it as a, doesn't matter, it implies the same thing. This is the rate at which the sample is decaying. So this rate becomes minus dn by dt, or it becomes equal to n lambda, n lambda, n lambda, n lambda, or you can write r is equal to r naught e to the power minus lambda t. If you want to write it as activity, a will be equal to a naught e to the power minus lambda t, where this a naught is the activity at time t is equal to 0. Do we understand this? A naught is the original activity. The units of radioactivity are becquerel, Curie, and Rutherford. 1 becquerel is 1 disintegration per second. 1 Rutherford is 10 raised to the power 6 disintegration per second. 1 Curie is 3.7 into 10 raised to the power 11 disintegration per second. Remember, the activity of this sample decreases as the number of nuclei decrease. This activity is inversely proportional to half-life. It is directly proportional to lambda. Therefore, it is inversely proportional to half-life. Sometimes we use this term specific activity. The specific activity is the activity per unit mass. The specific activity of 1 gram of radium 226 is 1 Curie, and that is why this Curie has a different disintegration per second. Activity after n number of half-lives. A after n number of half-lives will be equal to A naught divided by 2n. These are all the formulas of this particular section. I'll give you 2 minutes and then I will write all these formulas that we have done one by one so that you can write them together. So these are the different formulas that we have seen. The first formula is dn by dt or minus dn by dt is lambda n is equal to r is equal to a. You can write the same formula in this ln of n by n naught is equal to lambda t, or you can also write it as ln of activity A by A naught is equal to minus lambda t. I hope you are able to understand this. The third formula is written n is equal to n naught e to the power minus lambda t. You can also write A is equal to A naught e to the power minus lambda t. The fourth formula is for time written in terms of ln. The fifth one is time written in terms of log. The sixth one is activity. The seventh one is again activity written in terms of lambda and n. Now remember the different ways in which you can call lambda. You can call lambda as rate of decay, you can call it as decay constant, you can call it as disintegration constant, radioactivity constant, Rutherford Soddy constant, or the most important one, the probability of decay per unit time. I've seen a question come on this in JEE, so remember that. T half, the formula for T half, the eighth formula, the formula for T half or T half or tau is 0.693 by lambda. The ninth formula is T average. The ninth formula is T average, and T average is 1 by lambda. The 10th formula is T average is 1.44 times T half. You can also write this as ln 2 by lambda. I hope all of you are able to understand this. When n becomes equal to n naught by 2, time t becomes equal to t half. When n becomes equal to 0.37 times of n naught, t becomes t average. I hope you are able to understand this. I'll give you 5 minutes to note this down. Then this is a question that you will attempt. The half-life of a radioactive nuclide is 20 hours. Then what fraction of the original activity will remain after 40 hours? I'll give you 2 minutes to solve this. 1 by 4 is the correct answer. See, the half-life is 20 hours and they're asking us how many, what will be the activity after 40 hours. So n, which is the number of half-lives, will be 40 divided by 20. So the number of half-lives is 2. A is equal to A naught divided by 2 raised to the power n. So it will be A naught divided by 2 raised to the power 2. A naught by 4 would be the answer. These are the type of questions that you can expect in an examination hall. This is the next question and I'll give you 2 minutes to solve it. 15.75. is the correct answer. And how are we going to get this? It is given that how long does the activity reduce to 1/8. So the new activity is A naught by 8. So I can write it as A naught into 2 raised to the power 3. So the number of half-lives is 3. Number of half-lives is 3. The number of half-lives is 3 and the half-life is 5.25 years. So the time will be 3 multiplied by 5.25 and the answer will be 15.75 years. That is the correct answer. As you can see, the questions are pretty simple and pretty straightforward. There can be a tricky question here or there, but I think I have given you enough substance to tackle those tricky questions. This is the type of question that you can have in your JEE Advanced, probably not in your JEE Mains. Radiative decay is given by something. Only A is present at time t is equal to 0. Find the time at which, if we are able to pick one atom out of the sample, the probability of finding B is 15 times the probability of finding A. Probability, I told you something about that. So how are we supposed to do this? I will just give you a hint and I'll hope that after this hint, you might be able to do this. At time t is equal to 0, we only have A. With number, let us say n naught, B is 0. At time t is equal to t, the number of nucleus or nuclei of A becomes n. The number of nucleus or nuclei of B becomes n naught minus n. Now I'll give you 2 minutes again to solve this. So how are we supposed to do this? I already given you the probability of getting A. The number of molecules of A will be n. The total number of molecules is n naught. Probability of getting A is n by n naught. Probability of getting B is n naught minus n divided by n naught. I told you that. Now, probability of getting B is 15 times the probability of getting A. This is given in the question. So n naught minus n divided by n naught is 15 times n divided by n naught. I hope you understand this. Yes or no? So from there you can get n is n naught divided by 16. N is n naught divided by 16. N is n naught divided by 16. And that was the whole purpose of doing this exercise. As soon as you get n is equal to n naught divided by 16, you can write n is equal to n naught 2 raised to the power 4. So the number of half-lives, we have taken too much of time, is 4. Number of half-life is 4. So the time taken will be 4 multiplied by 8. 32 years will be the time when this thing happens. So that is how questions are framed and that is how questions are done. I will be extending this class, so maybe for 1 hour, maybe for 2 hours. So that is why at this point in time, after 2 hours, we are going to take a break. So I'm giving you a break for 5-10 minutes. Go back, refresh yourself, sit and see what we have done, because after this break, we are going to finish this chapter once and for all. We will be doing questions from the previous year papers, the January session papers, 2022 papers, and papers beyond that. And you will see that the questions are pretty straightforward. So be ready. 10 minutes. I'm giving you a break. Go back, relax, and then I'll meet you after 10 minutes and we will start from here. You get this? Okay. I'll see you after 10 minutes.